So I was talking about how you can determine the tactic transition temperature or Class A transition temperature. So the software will allow you to determine the tactic point by drawing that straight line where the line meets. Draw it down, that's the tactic temperature. And then class transition temperature again. You have to draw the tangent line there. Maybe tangent line there in between the halfway point. Halfway point is the glass transition temperature. So DSC is a really handy instrument that will allow you to determine all those temperature points. And then another important piece of instrument is called the freeze-dry microscopy. So you see the microscope, and then this microscope has a little freeze dryer on each stage. So there's a dry ice, and then there's a temperature control. So you can do the freeze drying in a very small, scale, because on top of your microscope stage, you can do your freeze drying of your drug molecule. So once you figure out your tactic temperature, glass transition temperature, amorphous temperature, all those things, then you can test drive your freeze drying process on this freeze drying microscope. Okay, so in that small scale. And while your drug molecule is being freeze-dried, you can take a look at the condition of your freeze-dried drug under the microscope, okay, using polarized light. Okay, so it is basically a mini freeze-dry on a microscope. It allows the technician to freeze-dry a sample in real time and watch it under the microscope. Okay, you can watch it under differential light. This technique allows the collapse temperature to be determined. At what temperature your drug will be collapsed, you can see that, okay, under the microscope. Okay, so that collapse temperature is again the temperature where the sample loses structure and can support its own weight. So you want to avoid that collapse temperature when you design your freeze drying point. So the freeze dry microscope is handy to identify that. Okay. So the small freeze dryer can be seen on the microscope stage, like I said right there. Okay, unit has liquid nitrogen line, which is this. Okay, connected to cool, and the vacuum line is also attached to that, and then the electric heating line is also there. So vacuum pool and the heating line. So all three lines are attached there. Okay. So if you look at it on the microscope, you may see something like that. So in deflected light condition, okay, you'll see different images. So the polarized light condition. So under that condition, you will see dried part of the drug will show up like maybe green color area, and then frozen drug condition will show up as this kind of colorful. I mean, blue is frozen, and maybe some interstitial space maybe, and then collapse, okay, is showing up as a line, kind of this structure. You can see that where the collapsing point is, under what temperature point. So it collapses at minus 36. I see that. You can see that. So you probably want to avoid the drying at minus 36. You have to probably do it on the lower temperature than 36, minus 36. Okay, so that's what you will use my freeze dry microscope. And then other equipment, of course, the freeze dryer itself is very important. Okay, whatever scale you have, inside of freeze dryer you will see these kind of units. Okay, so modern freeze dryer utilize the following system. Most important part is a condenser. Okay, that has extremely cold coil or plates where water vapor is created during sublimation. So remember, the water is vaporized through sublimation from your vial, and it's going to go and end up at the condenser area because there's a low pressure than the vapor pressure inside a vial. So that's where water will end up. But still, it's a cold temperature, so the water will be crystallized again on the condenser. Okay, that's how pure water will be collected on the condenser. And then temperature controlled shelf, of course, drug vials will be sitting on top of your temperature controlled shelf. So through the transmit of the temperature, so your drug will be also frozen. Okay, and the cooling unit, and this will freeze down. So there should be efficient cooling unit that will change the temperature of your shelf. Okay, so you'll need to have that. Cooling or heating will take place at the same time. The vacuum system, efficient vacuum system, should be there in your fridge dryer. Okay, and then controlling system, the software that will allow you to change the temperatures or change the vacuum pressures and the duration of those. So controlling system is of course required in your fridge dryer. And then your fridge dryer should be used under the CGMP condition, of course. So, cleaning and sterilization is a process that should take place before and after, between the use of a fridge dryer, right? So, cleaning and sterilization system is very important. So, when you do a CIP, clean in place, if you're thinking about the large scale, manufacturing scale, it's very, very large. So you have to clean inside. So CIP will take place. So normally, fridge dryer should have sprayable spray nozzle that will clean by pressurized the water shoot out, and you'll get rid of whatever the unclean contaminants that may be in there. And then after that, after CIP is done, of course, then SIP will take place, steam in place. So sterilization will take place inside of a fridge dryer. Okay. So you can use steam heat, or sometimes you can use vapor phase hydrogen peroxide to sterilize it. Okay. So either is possible. And the fridge dryer design, the model. Okay, fridge dryer may come in different sizes and different capacity. There are these types of manifold fridge dryers. So manifold meaning there are valve hookups. So if you have a large vial that has some kind of material that needs to be fridge dried, the mouth of the vial is hooked up through these manifolds directly. Okay, and the fridge dryer will take place right there. Okay, so it's not used for CGMP, but so it can be fridge drying your product. Okay, so precise control of sample temperature cannot be achieved if you use manifold fridge dryer. Okay, and it's normally used for non-GMP kind of a system. Okay, and then developmental scale fridge dryer. So if you are working in a PD lab, process development lab, and you are involved in developing a process, fridge drying process for the manufacturing group, you cannot use the large scale fridge dryer for your process. You will use something smaller to find out the best method, right? So this is what you use for. So developing a fridge drying protocol, you use kind of small, maybe a flow model. Okay. So you can establish best fridge drying cycles for the manufacturing group. Okay, so if you have that, so there's a condenser, there's a fridge dryer shelves, temperature controlled, your vials will be sitting there. Okay, that's how it works. But one unique thing that you can find from this developmental scale fridge dryer is something called sample thieves. Okay, so sample thief. Okay, so this sample thief will allow you to take a sample out during a fridge drying cycle. Okay, without opening up the entire chamber. You can maybe take out one vial at a time if you want to analyze maybe what's happening on your vial. If you want to take a look at it, without jeopardizing entire fridge drying cycle, you can just grab one vial out and analyze the fridge drying condition. So that's what this sample thief would do. So that may be a important feature for your process development process or purpose. Okay, and then pilot scale fridge dryer. So when you manufacture something for clinical trial, it doesn't require full manufacturing scale. Then you can use the smaller version of large scale commercial fridge dryer. But commercial scale, the large scale fridge dryer may be this big. It's very large. Okay, maybe thousands and thousands of vials can be fridge dried together. Okay, so the main flow of the fridge dryer is associated with the clean room. Of course, it's done inside of them. So the vials come out from the filling line, very clean ISO, maybe 100, class A, grade A condition, and then loaded into the dryer directly in the class A environment. Okay. So everything is done automatic, robotic arm loading system. So human interface is not involved there because of the contamination issue. Okay, and then there are three tray dryer types. So this is probably non-CGMP, but if you are using this for maybe food material or something like that, you can maybe tissues, food that can be dried. Maybe you may have dryer, food dryer at home. It's probably something similar to that. Okay, so then attributes of freeze-dried product. Okay, so once your vial is freeze-dried, your product is freeze-dried, what important attributes should they have? Okay, so number one thing is reconstitution time. So once it's all freeze-dried, when you try to use it, before you use it, of course, you have to reconstitute your drug by adding water, pure water only. So bring it back to solution, right? So when you add water aseptically, and how long does it take to reconstitute your drug? Okay, so the reconstitution time is very important. So that should be done easily within about 2 minutes of time or less. Okay, maybe just gentle shaking or just several inversion of your tube, that should be achievable. So that is very important. Okay. And then extend the stability. Once it's freeze-dried, of course, your shelf life will be extended at least like 2 years. That should be the benefit. Otherwise, there is no point of doing the freeze-drying because it's so expensive. Okay, so extend the stability. So you need to do the study on the stability of your drug and see if the extended time during the 2 years your drug is still safe and effective, active, right? And then appearance and pharmaceutical elegance. Okay, so the freeze-dried cake, does it look good? Does it give you the cake kind of condition, the white solid product, which is not destroyed, which is not floating in the vial? So you have to have the very elegant cake in your product. And then residual moisture. Okay, once freeze-dry is done, the moisture remaining in your freeze-dried product should be less than 1% of the total weight. Okay, so if it's more, then there's a tendency that your drug is still going through hydrolysis, so stability is being minimized, right? So make sure that you could achieve that less than 1% of residual moisture in your freeze-dried products. So we'll do this test in the lab 5 and 6. Okay, and then temperature and vacuum monitoring device. So in your freeze dryer, you have these monitoring devices. Again, these are kind of not really pharmaceutical, but it's more of I guess machine-related issues. But when you sense the temperature, what are the most effective, sensitive temperature sensor devices? And that's what you're talking about. You can use resistant temperature detectors, RTDs. And you have different metals in the wires in there, maybe platinum and inert ceramic support, inert sheath, and it can do very accurate reading by this design. The major advantage of using RTD is a linear response in regard to the resistance and temperature change, which makes the device very accurate and precise and makes calibration easier. So but this advantage of this RTD model is the temperature reported is a function of the temperature across the entire wire. Okay, so there may be variation somewhere. Okay. Another temperature sensor is called thermistor. Okay, it's just like RTD. It has wires. Okay, so understand, I'm not going to go into detail of this design of these sensors, but you can take a look at what different things are possible, available. So advantage of this thermistor is extremely sensitive to temperature change and give a large response to small change in the temperature. But main disadvantage is the response is exponentially nonlinear. Make them extremely difficult to keep within calibration. So there are pros and cons.